This is bonding video number 10. By the end of this video, you should be able to describe the unique or special properties of a water molecule. In order to do this video, you should have with you your video number 10 worksheet and a pencil. And as always, this will be due in class the next time that you have class. The properties of water. Water has dipole-dipole intermolecular forces, but these dipole-dipole forces are so strong it has a special name, which is called hydrogen bonding. The hydrogen bonding, and we've talked about this in the past, comes from one water molecule to the next. Now you don't want to get confused with a covalent bond. Inside the water molecule, right here, is a covalent bond. It is an actual bond. It is inside the water molecule and is an intramolecular force. The intermolecular force, with an E, inter, goes from one molecule to the next. It's in between. So right here is your intermolecular force, caused by a slightly positive and a slightly negative end attracting to each other. This force here is a dipole-dipole force, but being so strong, it has a special name of hydrogen bonding. Now, one thing to keep in mind is that hydrogen bonding is actually a misnomer. Misnomer means that it's been not named maybe as well as it should be. And the reason why: hydrogen bonds are not true bonds. They're not inside the molecule. It is not a covalent bond. And as a result, it's an intermolecular force. So hydrogen bonding, while it sounds like it's a bond, is not a true bond. The properties of water. As we said, the hydrogen bonding in water is an extremely strong dipole-dipole force. And it's this strong force that's holding the water molecules together. Because it is so strong, it is going to be harder to separate water molecules from each other than from a similarly sized polar molecule. Now this is important to state because, as we know, it's relatively easy to separate water molecules from each other. It's definitely easier than it is to separate ionic compounds from each other or metallic bonds from each other, but to be separated two water molecules and comparing that to other polar molecules, these are relatively hard to separate, and this is going to give it special properties. Okay, the properties that are different. Water has a higher boiling point and a higher melting point than you would expect for, once again, a similarly sized polar molecule. And the reason why is what we had just said on the previous screen. They're going to be harder to separate than what you expect because this bond, this attraction, is stronger than what you expect. The surface tension is also going to be greater than what you expect. Surface tension is the force that holds or pulls molecules together in the liquid so that the liquid takes up the smallest possible size. The diagram of this is as follows. If this is a water droplet, these are your water molecules, and they're attracting to other water molecules. This attraction goes on in all different directions. On the surface, these attractive forces right here are attracting water molecules to each other. And as a result, these attractions, the hydrogen bonds, pulls the molecules inward and causes you to have overall the smallest possible size. Now this can be seen in nature in many different places. For example, insects or spiders are sometimes able to walk across the surface of a pond. And the reason why is their mass is not strong enough to break through the multitude of intermolecular forces, the hydrogen bonds, that they would have to break through in order to go through the pond. So right here is the surface tension in action, and the insect or the spider can walk across the pond. Another example, this is a picture of somebody swimming, coming right out of the water. The picture's been taken that instant of time where you can see the water coating the head, and one water molecule is attracted to the next, creating that kind of sheen or coat over the front of the person's face right before it breaks through. Viscosity. Viscosity is the resistance to flow. An example of this is honey or maple syrup, which if you ever tried to pour before, it takes a very long time to pour from one container to the next. And the reason why is because all those molecules are attracted to each other more than what you would expect. For honey and syrup, there's a great deal of hydrogen bonding occurring inside the molecule. Water is similar to this. It has a greater viscosity than you expect for something else of the same size that's also polar. Now, you're thinking water is very easy to pour. What are you talking about? If you had a styrofoam cup and you had a very small pinhole in it, it would take water a relatively long time to drain through that cup. A little bit longer than what you expect for something else that's also polar in the same size, and you would see drops forming and coming out. The next thing is water has a greater density as a liquid than as a solid. This is very unusual. Solids are usually more dense than what the liquid is. As a result, you get the following occurring. This is liquid water molecules. They do have some hydrogen bonding occurring from one water molecule to the next, but because it's in the liquid state, the water molecules are able to move about, back and forth. And so occasionally you get times when you have two negative ends or two positive things in contact, but it's short-lived and it keeps flowing through. You get no crystal lattice forming in this case. But as ice or as solid, these hydrogen bonds have to form perfectly. You can't have two negative things in contact with each other for any extended period of time, or two positive things. So over here, since they're going to be stuck in place, they're going to be ice, you have to have positive to negative, repeating structure. And when that happens, you get a crystal lattice shape. But density-wise, you see all this empty space here versus not as much empty space here, and this causes a lower density. Because of the low density, ice will float on top of the ponds and the lakes in the wintertime as they freeze.